missed something. One thing that's also really kind of important, oh, I did add it in, is that it's a strong nucleophile. If it's not a strong nucleophile, right, it can't initiate this attack. So one thing that's kind of important for both bimolecular reactions is that the nucleophile is pretty strong. You'll realize here, I only really use strong nucleophiles. So what do you want to take from these classic examples that I've given you? Well, really all I did was I did the primary, secondary, secondary with a group next door, and the tertiary examples. All I want you guys to realize is these nucleophiles are simply just substituting on the spot that they're at. So a primary example is just going to substitute. This is the exact same you'd see for a methyl, right? Like I could get rid of these carbons here. I could get rid of these carbons. Nothing would change. This exact same reaction, right? Same thing with secondary. On a secondary substrate, even though there is a little bit of bulk on that center there, right? Something like a CN minus can go ahead and still engage in an SN2 attack, right? This one's really an important one, right? The fact that a dashed iodine, so if the bond is a dash here, right? After the reaction with CO2 minus, which is this whole group here, it becomes a wedge. Okay, it becomes a wedge. Now here's actually, and I'll include this too. This does not mean that if this molecule is S, that this molecule becomes R. That could be the case. Really, the only thing we're observing is that the bond stereochemistry changed. We're not at all observing that R and S is flipping. There is definitely examples that I can think of and I can make where the bond stereochemistry does change from dash to wedge, but it goes from R to R, S to S. Those examples exist. Again, the most important implication is simply just this. If this is dash, it must be wedge after SN2. Okay, it must be wedge after SN2. Now, the last example here that's I think is kind of important, even though it's not an SN2, so I wrote this in here, it's not an SN2. Don't think that this reaction here is NR because it's so slow. The only thing that's not working here is the SN2 mechanism. This can't be an SN2. If this were a chiral center, we would not observe at all an inversion. We would observe a completely different mechanism. Again, I haven't even started the SN1 slide yet, but it'll be in the SN1 E1 slide when I get to that. So then when we get to E2, which is really, honestly, I think E2 is the scariest reaction because there's so many different examples of them. E2 has quite a bit of observations that have to be made. Okay, and so again, someone just took a nucleophile and took an alkyl bromide or alkyl halide, add them together, and they just observed what they saw. What they saw was that when they added these two things together, they got an alkene, they got a protonated nucleophile, right? And they got the leaving group, which is the bromine, right? And again, they just noticed, okay, if we increase the nucleophile concentration and the substrate concentration, right, what we get is increased rate, right? So it's clearly bimolecular. But here's where things get a little interesting. What they noticed was that not only was the alpha carbon involved, right? So not only was the alpha carbon substitution involved, but the beta carbon was also involved. As you increase the number of beta carbons, you also increase the number of product concentration, that alkene product. The more beta carbons you have, the more likely you are to create this alkene product. Okay, so that's kind of like an interesting kind of concept here, because back here, we said that if we had increasing of these alkyl groups or like beta groups, right, SN2 kind of slowed down. Well, here, the more beta groups we have, the more likely we are to have an E2 reaction. Okay, and again, one thing I want you guys to notice here is you see how I put these arrows here, or like these less than signs here. Notice how this is the only guy without a beta carbon. It turns out this substrate will never do E2. It will never do E2 because the beta carbon is incredibly important. Why is that beta carbon important? Because when we look at the mechanism, so this is actually enough to already explain the mechanism. If the nucleophile is coming out protonated from this reaction and we're forming a double bond, right? That must mean the nucleophile is taking a proton from this beta carbon. Okay, let's add that in actually. So it's taking a proton from this beta carbon, shifting electrons between that alpha and beta carbon to form a double bond. And then the alpha carbon loses the bromine, okay, loses its leaving group, which is that bromine. Oh, I realized I didn't even change it here. So that must mean then that any elimination reaction we think of is going to be an alpha beta reaction. It's an alpha beta reaction. Again, I know Levens calls this alpha. Just please believe me, it's alpha beta like this. When you take Nassiri next quarter, you will have to know it's alpha beta like this. So just write it in your notes that Levens just writes it weird, but for Nasiri, you do need to know that it's this way. That's alpha beta like that, because in class, when you guys talk about alkenes again, she's going to refer to them as such. Okay, but this is going to be alpha beta reaction. Okay, an alpha beta reaction. That's why this reaction never works, because there's no beta carbon. So if there's no beta carbon, how in the world is a methyl substrate ever going to react in elimination fashion? Okay, so if the nucleophile is taking a proton, right, so it's getting protonated in this system, it not only does it have to be strong, it also has to be basic. So you'll notice some of these examples here that I have in the classic examples, you'll notice it's OH minus, OR minus, C minus, N minus. These are all classical bases. Okay, these are all classical bases that we would typically see. Okay, so a lot of times if you see a base, it's very likely you're going to do some kind of elimination reaction. Although again, if we have this substrate here, not very likely. Okay. Now, one other observation, before we start looking at the classical examples, there's a couple more observations we can look at. One observation that's kind of important is that if we looked at a chiral example, the bromine, okay, so this bromine here, if it's a wedge, the hydrogen that we end up taking in the reaction ends up being the dashed hydrogen. So essentially, there must be some transition state, which is what we see here, the anti-periplanar state. There must be some transition state between Br and the hydrogen that we take. So it's dash and this is wedge, in order for elimination to occur. So that's something we should take into consideration whenever we're doing reactions with chiral centers. So a couple of these we can actually already look at before we look at some of the more observations. But if we look at some of these reactions, again, if we do the primary example, right? Primary, it turns out if we use a basic nucleophile, which is, again, what we would want to do an elimination reaction, a basic nucleophile would mainly give us a substitution reaction, but there is a minor product of an alkene. So Levens is very notorious for asking you to predict all the possible products. In other classes, you'll just be asked to predict the major one. If Levens ever asks you to predict the major product, it's very important to understand if we use a basic nucleophile, even in a primary substrate, you will get both a major and a minor answer. Okay, so it's not only a strong nucleophile, but a basic one. You can kind of contrast this to the first one up here. RSH compared to OH minus is not basic at all. So that's why we only see one product here, is because this is not a basic nucleophile. This here, though, is a pretty basic nucleophile. So we do get, a minor product of this, although it's minor. However, once we start adding in bulk, so we get to the primary hindered example. So just adding this alkyl group here suddenly makes both of these major. Okay, it makes both of these major. So once you add in a little bit of sterics, you immediately start to make more alkene product. As we move down in substitution, secondary and tertiary, again, as you increase those beta groups, basic nucleophiles are never going to substitute. Okay, they're never going to substitute. You're exclusively going to get eliminations. Okay, you exclusively get eliminations. So primary is the one where you would have a minor amount of elimination, but once you get primary hindered, secondary, and tertiary, practically it's practically going to be all alkene. And this is not like a 50-50, I would say. I'd say it's more like a 60-40 or like a 70, or yeah, like a 60-40 is what I would say. Definitely going to be more of this, because the more bulk you have, right, substitution starts to decrease in concentration. Substitution product, it's not really favored whenever you have a little bit of bulk. Now, these examples here are just renditions of these examples up here, but there's a little bit of difference. So this bromine here is a secondary bromine, just like this one, but this bromine was symmetrical. So it didn't matter which beta carbon I interacted with, right? As long as I interacted with one of them. But now this one is asymmetrical, where one is methyl and one is an ethyl. So this is a methyl side, and this is like a primary side. Okay. If we are to look here, there's a couple more observations we can make. Okay. One observation we can make is that the type of beta carbon we interact with can actually tell us about the product, what products we're going to make and how many of them we're going to make. For example, if the beta carbon is a CH3, okay, so if it's a methyl carbon that we're doing the elimination on, we're going to get 3 products because there's 3 hydrogens here. Okay, now you might think, okay, wait a minute, these 3 are the same, right? So it's really one product, and that is the truth. This is all the same product, so you would only write it once. But it's important to understand that either one of these protons could be taken, As long as they're trans, right? At some point in time, one of these H's will be trans to Br, okay? And either one of these products can form. Luckily for us though, all of them are the same. So we just write one. But the number of hydrogens are directly correlated to the number of products we make. And this is way more visualizable in the beta, in the CH2 example. So when it's secondary, because when it's secondary, I do have two products, right? Because I have two hydrogens here. Either one could be trans to Br. But what you'll notice is that one of these is a trans alkene and the other is a cis alkene. So if you're ever doing an elimination on a CH2 side, okay, on a CH2 side, you know that one answer will be trans and one will be cis. Now, in general, again, this is up to Levens, right? If she writes all products a major or all products or just major products, if she wants all products, make sure to get both the trans and the cis alkene. Okay. If she writes major, typically the trans one is major. Typically trans is major for these reactions. But again, it's really a mixture. It's really up to chance, really. I think the product distribution ends up being like, I think it's like another one. This one's we're more closer to 50-50, I think so. So it's up to her what she tells you in class. But if she says all products reacting with the CH2 is going to give you two answers. If you react with a beta carbon that only has one hydrogen, so there's only one here, just like the last two examples where 3 hydrogens give us 3 products, 2 hydrogens give us 2 products, 1 hydrogen will only give us 1 product. And this product is very, very specific. Okay, it's always just one product that we get. And this will very much boil down to what is the exact stereochemistry of that system. Okay, because I didn't show it in, but it does matter whether this bromine is a wedge and if this is a dash or a wedge in its current state. Now, hopefully you've been, paying attention and realizing, hey, right, there needs to be a beta proton, right? Like the whole way this mechanism works is if I take a hydrogen off the beta carbon. If there is a system example where there is absolutely no beta hydrogen, so this is like tert butyls on both sides, it doesn't matter what you do, this reaction is always going to be no reaction. Nothing will result. Okay, so we can actually take some of these observations here and apply it here. There's just one more thing we have to add in. Okay, it turns out that there's an extra level to this. Not only can you predict what the product will be based on what beta carbon to react with, but let's say we have an asymmetrical example of like the one we have over here, right? Where we have a beta 1 that's a CH3 and a beta 2 that's a CH2. Well, it turns out if we use a small base, okay, small bases give us reactions with the more substituted carbon. So notice how the CH2 is the one that we end up reacting with in the small base. But the bulky, if we use a bulky base, so a really big base, there's 2 examples of this, and I've used them in this side here. That ends up reacting with the less substituted carbon, or the beta carbon 1, right? The CH3 on this end. And again, right, this is a CH2. That's why we get 2 products. This is a CH3, which would give us 3 products, but they're all the same. So I only wrote it once here, although I did write it 3 times here, just so again, you understand that it's 3 different products we could make. So if we apply it to, this system here, this is an example. So this is like butyl lithium, and butyl lithium just looks like this. I guess I could have just wrote it in. And butyl lithium looks like this. Okay, it's a carbon with a minus charge on it. Just like that. It's a classical example of a strong base. This strong base will react, right? It's a what we would call a non-bulky base. Okay, so it's a small base. This small base, if it had to choose between CH3 and CH2, is reacting with the CH2. And so that's why we get the cis and the trans isomer. This guy here is tert butoxide. Tert butoxide is one of 2 examples of a big base. Another example of a big base is LDA. These are really the 2 examples you want to know for big bases. This big base is only going to react with the CH2 here. Okay, it's going to react with the CH3 here. So that's why we get the terminal answer. Okay, so asymmetrical E2s we can predict very easily as long as we know, right, how many products should exist for either beta carbon and which beta carbon is the one that we're going to select for based on the kind of base that we use. Okay, now if we use an example that has stereochemistry, so notice how this H here, oh, sorry, this should be, let me just check this real quick. Yeah, sorry, I'm going to change the stereochemistry real quick. This should be hash, this should be wedge. This should be wedge, just be hash. There we go. Oh. Okay. If we look at an example where we have a stereo center, right? Both of these are stereo centers here. Again, whenever you have one H, it's very, very specific. You have to look at the anti-periplanar state, okay? Because there's only going to be one possible answer. If we look at this example here, again, we're using a small base. So if we're using a small base between beta 1 here and beta 2, right? This is a CH3, this is a CH. We're going to go with CH because small bases select for the more substituted carbon. If you look at this I is a dash, this hydrogen is a wedge. Basically, if I wanted to predict the product, all you're really doing is you're getting rid of the H and you're getting rid of the I, and you're just making the double bond as presented. So you realize if you look at this and this, it looks kind of exactly the same, right? The only difference is I took out the stereochemistry and I put the double bond. The reason for this is because this is the anti-periplanar state. And so when H is taken, so when H is going away, right, and I is being removed, the double bond is literally just being formed like that, okay? The double bond is being formed like that, and we're just planarizing on that carbon there, just like that, okay? So if it's already given to you in anti-periplanar state where this H is a wedge, this I is a dash, or the opposite, you can just redraw everything without the H and the I and just put the double bond there. Now, here's where things get a little interesting, right? Here, in this case, I and H are on the same side. So they're not trans anymore, they're now cis, okay? How do you predict the product for this? Very simple. All you do is you redraw, you redraw, so you have to get rid of these two groups here. You can draw the double bond. But now, instead of keeping this orientation here where this ethyl is down here, you just switch it. So these two problems here, where I and H are trans versus cis, they should never make the same isomer. It should always be different isomers. Otherwise, we wouldn't really care about anti-periplanar state if they made the same answer. So if they are trans already, you can just draw what you see, right? You see that the methyls are trans to each other and that the ethyl is on this side. It's like cis to this methyl. So that's how we get this alkene here. Or, right, if they are cis to each other, you can draw what you see, just flip one of the sides, okay? So we can, get rid of these two groups here, right? Oops, get rid of those two groups there. We can draw this alkene. How do we make this the right answer? All we do is we just switch the place of the ethyl and the methyl, and that's how we can predict that answer there. Okay, these are probably going to be the hardest ones on your exam. She's definitely going to ask them because I think I saw them in your problem set when I was helping someone with it. So definitely you're probably going to see at least one or two of these examples where it's going to be already trans and not trans, and you have to just switch the groups. It's either you keep them the same or you switch them when you're doing that reaction. Now, again, these are small bases. And if we use a small base, that's why we reacted with this CH and not with this CH3. But if I use a bulky base like LDA, it doesn't matter what the stereochemistry is here. So that's why I put any here. It could be dash or wedge. LDA is reacting with the CH3 because it's the non-bulky, or sorry, it's the bulky base. So it's going to react with the CH3 side. It's going to react with the non-steric side. And that's why we're always going to get this answer here. Again, this could be any stereochemistry. Really doesn't matter what it is. Okay. And so these are always a really nice one to get if you get them. Now, I just did a couple of complex, I just did an example like that was a little more complex so that you have you get a little more practice seeing this. But again, notice how we use N-butyl lithium. Okay. So if we think about the beta carbons here, there's this beta carbon, there's this beta carbon, and this beta carbon. Of these three, the only one that has a hydrogen and is the most steric is going to be this one here because N-butyl lithium is a small base. So we're going to react with this hydrogen here. This hydrogen's a dash and this bromine is a wedge. So that means that we're already in anti-periplanar state. We can just get rid of these guys and just draw the double bond in. And that's exactly the product that we see over here, right? We just got to planarize this and planarize this. That's exactly the answer that we have right over here. Okay. So again, if it's already an anti-periplanar state, you are visualizing the alkene product. You're already visualizing it. You just got to put the double bond in and get rid of the stereochemistry. Now, if they're not trans, right, let's say they are cis, like in this example here, right, they're both wedges. Again, all you have to do really, you can do the same thing, right? Draw the double bond in and planarize these. Just switch one of the sides. You could switch this side or you could switch this side. Again, it's really up to you. I'm just going to switch the right side and there you have it. That's the product there. Okay, so this is just a little more of a complex one with more moving parts. Again, really wouldn't matter. Now, if we were to do this reaction with a bulky base, which I guess I could include that example as well, the bulky base, right, is going to react with the less steric side. So if this was the most steric side with the hydrogen, this is another beta carbon, this is another beta carbon. This is the beta carbon we're going to react with if I use something bigger. So for example, if I use like, I guess I can get rid of this example here. Oops. So let's say I used LDA again. The side that we're going to react with is going to be this methyl here. So we can get rid of this bromine here, and then this methyl will planarize. That'll be our answer just like that. This stays exactly the same because it never reacted, so it should never change, right? So it's just going to chill out. But if I use something like LDA, this is the beta carbon that we're going to react with, is the one up here. Okay, so that's kind of how you predict the E2s of like linear molecules. And again, really, for some of these, I want you to realize is, you know, especially the ones where they were already cis, the reason why we could do the reaction still is that even though this is cis, we could always rotate it. Okay, we can always rotate it because this is a linear molecule. Rotation is available. I guess if you wanted to see the rotation, right, all you're really going to do when we're rotating this molecule here so, let's make this the wedge and this the hash. This is bromine, this is methyl. You have this here. If we want to rotate it, I can keep the bond stereochemistry the same. So I can keep this wedge right down here, this hash down there, and this plane bond there. So that can stay the same. I just have to move everything in an order. So if I wanted to, I could move H to the back, so this dash here. So H can move back there. That would move this ethyl to the plane. So ethyl will go to the plane. And if H was the first thing to move, then this isopropyl is going to move to where the H was. Okay, and this is what it'll look like. Okay, so that's a way that you can apply rotation. You kind of realize I kind of ignored this group here. I really only moved 3 things. That's something you can do if it helps you think about it, is you can kind of ignore one of the 4 groups and then move the other 3 in accordance. So if H is moving to the dash, right, that's kind of like if you think about it, it's kind of like a, let me draw that in actually. That's kind of like a counterclockwise move. I can kind of ignore all this here. That's kind of a counterclockwise move. I can then move this up here, right, this ethyl to the plane, and then move this isopropyl down to where this is a dash. Okay, so that's a rotation that I can make. Again, 3 things can move, right, as long as you ignore 1, but you can't move 4 things at the same time. Okay, or nor can you move 2 things at the same time. It's always 3 things have to move if you can do a rotation. Okay, and so if we do it from here, now this Br and this H are in the anti-periplanar state. Okay, and then I could do the thing where I kind of just, get rid of the H and the Br, right? I give them a double bond and then I planarize everything, right? And if you look, this is exactly the answer that this one is. Okay, so linear molecules having the ability to rotate means that anti-periplanar state is always a possibility. You can always have anti-periplanar state as long as there's a beta hydrogen somewhere. Okay, so linear molecules can always rotate. Very important deal. There is only really one example where it's NR for E2, and that's when we have this here, right? When we have this molecule with no beta proton. Okay, now ring molecules are kind of interesting because rings have rings lack the rotation that linear molecules have. Okay, rings can't rotate, and so that means that whatever stereochemistry you see, that's absolute. So if I have this molecule here where bromine is a wedge and its beta carbons have these wedge methyls here, that means that the hydrogens that are beta here are going to be dashed. Okay, so these are going to, oops, not that. These are going to be dashed. So this hydrogen, those are going to be dashed. Okay, again, these are anti-periplanar. That's why we can see a reaction. So this is symmetrical, so it doesn't matter what side it reacts with. You know, this case, it'll just react. I think I did end up doing it with the right side, so it'll just react with the right side. Okay, but this H here and this bromine are always going to be trans. You can't really spin them to be cis to each other. The great counterexample to this is if I, switch the stereochemistry. So now that the methyls are dashed, meaning that these H's are wedged. If we look here, right, now the H and the bromine are cis. There's no way I can apply a rotation so that H can go to dash. Okay, H is always going to be wedge here. It's always going to be wedge. And because it's always going to be wedge and bromine is wedge, again, these are anti-periplanar eliminations. The beta hydrogens have to be trans to the bromine. If the only beta hydrogens are cis, there is no reaction whatsoever. Okay, no reaction can take place on these cyclic molecules. Okay, if we have here this molecule here where one side is hash, right, and one side is wedge, so one side dash, one side wedge. Again, we can draw in the H's here, but it shouldn't surprise you that it's only the left side where we have a trans relationship between H and bromine that reacts with this base here. Okay, it reacts with this base here, and what we get is the answer on the left side. Notice again how this methyl retains its stereochemistry because it didn't react. Where things get a little interesting is really this example down here. This is just reiterating the point of if this hydrogen here, right? If this hydrogen here is wedged, right? Again, these are cis. So even though I use a non-bulky base, it won't react on the right side like you might predict. It'll only react on the left side. This could have been any base really. I just chose to make it the non-bulky. But only the left side here has, again, a trans H. And so that's why the left side is the one that reacts. The most interesting example, I think, is this one. Because if you look at this one, you might think it's NR. Because you might notice, oh, the hydrogens here would be wedge, right? These would be wedge. So these hydrogens are wedges, right? This bromine is a wedge. So you might think that there's no reaction here. But there's also a beta carbon here. So not only is this beta carbon, this is a beta carbon, but this is also a beta carbon. This is the beta carbon that ends up reacting to this reaction, and what we get is this. Okay, so for E2 reactions, it's a little complex. You definitely want to sit down and do a couple of these, and definitely write some of these down. The easy ones, again, it's basically looking for a basic nucleophile, and all these nucleophiles that I use here are like what you would expect for basic nucleophiles, right? So N-butyllithium, ethoxide, hydroxide, LDA, amide ion, what else they use? Methoxide, right? These are what you would expect as basic nucleophiles. These are the nucleophiles you're looking for if you want to do an E2 reaction, okay? These nucleophiles up here that I use for SN2, these are not basic at all. So if you ever see any of these, it can't really be an elimination that's going on. It can only really be an elimination if you have one of these guys here. Okay. Now I am still working on this, so I'll get it. I'll get it done by tonight probably, or tomorrow, and I'll send it out. But it's meant to mainly be like a summary sheet kind of thing. But one thing we can do, okay, and it kind of feeds into the next question, is then we can kind of ask ourselves, right? Like, what else, how can we summarize all the reactions for, predicting the products? And so we kind of just made a statement earlier that, basic nucleophiles kind of do elimination, okay, and non-basic nucleophiles don't do elimination. So we can actually split up. We can sort of make a chart here where we have like nucleophile type. Okay, so what kind of nucleophile we're using, and also what kind of substrate we're using, and we can make guesses as to what the reaction is gonna proceed as. So let's say we have a methyl substrate, which is like CH3X, primary substrate. So I'll say unhindered primary, which is like CH2, CH3. Or let's just do this one. Yeah, CH2, CH3, X. We can have hindered primary, which is almost the same thing, just some like beta action going on there. And then secondary, which looks like this. And then tertiary. Let me actually move this up a little bit. and then tertiary, which looks like this. Okay, and we can cross-reference it to the types of nucleophiles we've been talking about. So we kind of talked about two nucleophiles today. We talked about non-basic strong nucleophiles and basic strong nucleophiles. So another way of saying this is, another way we can say this is like weakly basic strong nucleophile and strongly basic strong nucleophile. I'm just going to make a note here that this is going to be for the small bases. Okay, and then we can make another category here for the big one. So strong basic strong nucleophiles that are bulky. Okay, all that really leaves is what we would have talked about for SN1 SN2 or SN1 E2 or E1, sorry, SN1 E1, which would have been just weak nucleophiles that are also weak bases. Okay, and let's go ahead and let's partition this out. Okay, and we can start to answer some of these. So some of these we already actually kind of answered. We spent a lot of time on the E2 section, and we talked about how strongly basic strong nucleophiles like to do E2. So for secondary, tertiary, and for hindered primary, E2 tends to be a major product, okay, for these strongly basics. Okay, we know that SN2 kind of competes here. Okay, so both of these will be major. Okay, so I'll put here major and major. Okay, for these two, it's only E2, so that's what the major product would be. Okay, however, for methyl and unhindered primary, right, SN2 and E2, they kind of both show up, right? Or really, this one's only SN2, but SN2, E2 also kind of shows up here. The only thing is that this is major, right? And that the E2 is minor. Okay, so we have minor product of E2. Again, it's strongly basic, so it still has affinity for proton, and E2 is like a proton reaction, right? Because the first thing we're taking is a proton and forming that double bond. So if we have strongly basic strong nucleophiles, right, we should expect, right, SN2 for methyls, and then once we start, adding in beta carbons or beta hydrogens, that's when we start to kind of expect a little more E2 action. And you can it's kind of like a transition, right? You can kind of know it's like SN2 is major, and then once we get to hindered, it goes E2 is major. Okay, it goes E2 is major, and then SN2 kind of just like fades out after secondary and tertiary. I guess you could say SN2 is like minor in secondary. It's like it kind of shows up, but it's so minor. It's such a small percentage. It wouldn't be worth considering. You wouldn't really even say that a secondary halide has an SN2 answer if we use a strongly basic nucleophile. Now, to contrast, weakly basics are never going to do eliminations because they're weakly basic. They don't like protons, right? So one thing you can kind of tell yourself is that this is a no H plus type of reactor, and this is NH plus type of reactant, right? Because these guys like protons, these guys don't like protons. So remember, right, if bimolecular reactions are dominated by strong nucleophiles, and one bimolecular reaction requires that you have an affinity for proton, and these guys don't like protons, right? Weakly basics are never doing E2, never. They're never doing any elimination reaction. You're really only seeing SN2 reactions out of any of these guys here. Okay, so SN2, 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 SN2. You might remember, though, I made that little note that tertiary is so slow that SN2 is not the reaction we observe. Really, the reaction we'll observe is SN1, E1. Okay, so these will be like SN1, E1 reactions. All that really leaves then is going to be the bulky bases. Here's the thing with bulky bases. Bulky bases, not only are they, hindered, and they like to do that less substituted product or that less hindered side product of the alkene, they also almost exclusively do E2 reactions. So not only do we never see like, you know, substitutions, the only one that does a substitution is methyl, right? And the reason for that, right, is remember, for elimination, we need a beta carbon. Methyl substrates don't have a beta carbon. They only have an alpha carbon. So maybe I'll actually even label that, right? There's only, right, these have alpha beta, this has alpha beta, this has alpha beta, and this has alpha beta. But the methyl substrate only has, right, an alpha carbon. So if there's no beta carbon, in what world is the methyl substrate ever doing E2, right? Can't do that. You can only do SN2. Now, we didn't get this today, but, or we didn't talk about this yet, but when it comes to the poor nucleophiles, which, you know, you can kind of tell yourself, make carbocations, just remember that carbocation stability is kind of what dictates these reactions, or the ability to even make one. Methyl in primary unhindered will never do this reaction. So these guys will never do it. And these guys will never do it. For hindered primary, you can have what we call a concerted hydride shift, or like a concertive C+ shift. It can be hydride or methyl. The two substrates you're thinking of here is like this one and this one. So these guys can do it. It's just kind of a very specific example. It just concerted instead of stepwise. But these guys here will do SN1E1. For secondary, you just have to kind of look out for the carbocation shift. And for tertiary, it'll just do SN1E1. You don't really see carbocation shifts or SN1E1 on tertiary substrates, but there is an example that I can think of. You just haven't, you'll never learn it in this class. Now, we actually do have like a blank spot here. And this blank spot, I guess I kind of just want to, you know, it's not going to be any correlated to this, but I guess like what I could do is I could write out like what is a weakly basic, what is a strongly basic, and all these guys. So that's what I'll do in this section here. Again, I do want to, let me try to segment it because I don't want you guys to confuse it as part of the graph. So let me redraw these lines here. So we can do like this. All right, and then what we can do is for weakly basics, like strong nucleophiles, what do we expect, right? These are your halogens. So I guess I'll write them out, right? Br minus, Cl minus, I minus. Anything that's like really big is a weakly basic nucleophile. So sulfur in both of its charge states, whether it's neutral or anion form, will do it. Phosphorus, whether it's neutral or anion, will do it. Cn minus will do it. N3 minus will do it. Carboxylate ion will do it. Although it's kind of weak, it's not the best one. And that's all I can think of for right now. Oh, and then neutral amine will do it. So neutral amine will do it. If we're thinking about strongly basics that are doing these reactions here, okay, again, these are like your OH minuses, your OR minuses, your NH2 minus, your NRH minus. Okay, I'll put C minus here, but I do want to put that there's like, this is like an exception. So don't use it very often. It's not the best thing to use. It's better to use these guys here. N-butyl lithium is fine if you're trying to do an E2, but if you're trying to do an SN2, N-butyl lithium doesn't really do SN2, so I'll say no SN2 really. It's not a bulky base though, so that's why I don't want to call it a bulky base, but it won't do SN2 for sure. A bulky base, there's only two of these guys. That is going to be LDA. And then tert butoxide, which looks like this. And then poor nucleophiles, there's only really like 3 examples of this. Alcohols, water, and carboxylic acid. Okay, these guys are what you want to think of when we think of, oh, I should just write just this. Weak nucleophile, weak base. These are what you're thinking of when you're thinking of, you know, the guys that only really do SN1 and all that. Okay, cool. So we can go ahead and predict reactions based off of that. Cool. So I mean, once you're able to predict the reaction, then you just kind of have to apply the logic of, you know, what you need to know. So I guess I could also include here is to remember that inversion can exist, right? So on secondary centers, there's definitely going to be an inversion, right? An inversion that can take place, right? You really wouldn't see it for any of these guys because they're not chiral. Remember, SN1, E1, this is going to be more like racemic, you know, possibly. Just like these guys here, probably going to be racemic. Okay. Cool. So I guess maybe then we can look at a couple of problems we can do. If you guys want, I'll keep this up for like 5 seconds. You can take a picture of it right now. I'll wait like 10, 20 seconds if you need to take a picture or something, and then move on to the next page and kind of just do some problems. All right. I counted 20. I'm not sure if that was too fast or not, but hopefully you got a picture of it. So we can just kind of do a couple of problems here. All right. Cool. So I'll do like the first two, kind of like to walk through them, and then, you know, I'll ask more participation from you guys. But here's what I would do with the chart and with, you know, problems is I would first look at the substitution, okay, of the carbon holding the leaving group. So the substitution here, that's a primary. So that tells me that I'm going to be in the primary, you know, column. The row that I'm going to look at is the row that corresponds to the nucleophile. Here, I know that I put DMSO here, but DMSO is not a nucleophile, that's a solvent. The nucleophile here is going to be Cl minus because NaCl is Na plus Cl minus. So I know I have Cl minus and I have this guy here. So what I'm going to do is I'm going to go back here and I'm going to say, okay, I'm in the primary section. It was primary unhindered. So I know it's going to be here. It's going to be one of these guys here. Then I just look for Cl minus, right? Where do I see Cl minus? Cl minus is right here. right? I'm going to be in the orange column. So this guy and this guy is going to be an SN2 reaction. Okay. Since it's primary, I don't have to worry about inversion, like showing it. It's just going to happen. I know that the answer is going to be this. Okay. So I'm going to expect something like that. So, you know, kind of do the same thing here, right? I'll look here, you know, what is that? That's primary. I guess I can say that this is unhindered, right? This is clearly primary hindered, right? It has that beta branching there. Again, then I look for where this nucleophile is. You will sometimes, you're actually going to see this a lot where there is a nucleophile on the top and there's also a nucleophile on the bottom. And we can actually categorize both of these as to what kind of nucleophiles they are. But let's just go to the back here, right? So we know that we're in primary hindered, so we're somewhere here, right? What were the two nucleophiles? Remember that like the metals are basically just positive charges. So you can kind of get rid of this and think O minus if it helps you. Right? Same thing here too. If you wanted, you could have gotten rid of Na and just put minus here. It would have been exactly the same thing if you think about it. So there's an O minus and there's an OH. Okay. Where do we see O minus or O like OR minus? Right? We see OR minus over here. So that's a strongly basic strong nucleophile. We also see ROH down here, which is a weak nucleophile, weak base. So we have simultaneously. So there is a what strong base strong. Sorry, this is a weak base, weak nucleophile up here. We have a strong base, strong nucleophile, and a weak base, weak nucleophile, right? Which one of these two are we going to choose, right, to direct the reaction? In general, strong nucleophiles are what are going to direct the reaction. So we're going to go ahead and choose the strong nucleophile and see what effects it will have. So strong base, strong nucleophile. We have a hindered primary. So this one here, right? We're going to have both SN2 and E2 major. Unless Lieben's told you different, I'm going to put both answers here because both are likely. So we're likely to get the substitution and we're likely to get the elimination. Now remember that elimination is you know, it's going to be off the beta carbon here like that. So we can just make the double bond here like that. Okay. There's only one beta carbon, so there can only be there's only one beta H, so there's only one product. Okay. So again, if we just kind of do that, we can solve all of these. So then I just have to add, so then let's get, I guess, a little more participation here. So what is the substitution of this bromine? Would you call it primary, secondary, tertiary? Yeah, it's secondary. So we know that we're going to be in this column here, right? And then if we look at, right, the nucleophile, right, which is just methanol, right? Where do we see methanol here? Yeah, it's a weak nucleophile, weak base. Okay, so we're going to be in this column here. We're secondary, right? It's going to be an SN1E1 reaction. But look at this, right? If it's SN1E1 for secondary, we have to look out for a carbocation shift. Okay, so it kind of helps if you kind of think of the mechanism here. The carbocation would look like this, right? When the Br leaves, should we worry about a carbocation shift? What do you guys think? Yes, we should. You're totally correct. We should. Why should we worry about a carbocation shift? Because anytime a secondary cation is next to a tertiary carbon, okay, there's always going to be a shift. There's always going to be a shift just like that. Okay. And so we're going to form this cation here, which means the actual answer is going to be this guy here. Okay, that guy there. So always be on the lookout for that. This is like so classical. It's always going to look something like this, where a secondary center is next to a tertiary. You see that weak nucleophile, you know exactly what to expect, the carbocation shift. Okay, so maybe I'll even write it here, right? Watch out for secondary to tertiary carbocation shift. So secondary is next to tertiary, or actually it could be next to tertiary or quaternary, right? Quaternary would just be if it's a, you know, instead of being a tertiary center here like this one, if it were just this, then the case would just be that methyl shift over. It would just look like that. So that's how that's the only way it changes if you do the methyl example, if you do the quaternary example there. Okay, just kind of get rid of that H. So I'll just keep it changed like that. But, you know, if you need to see that last one, it's in the recording. So cool. All right, look at this one here. What kind of center do we have here? It's going to be secondary. And then this is a C minus, right? So where do we see C minus on here? So we're secondary. Where do we see C minus? Yeah, it's going to be strongly basic. So secondary, strongly basic, that's an E2 reaction. We are definitely going to see an alkene. Now, this is a small base. This is a small base, and we have two beta hydrogens, right? We have a primary center, and we have a primary center, and we have a secondary center. Which center are we reacting with if we're using a small base? Or sorry, strong base, strong nucleophile, that's small. We're going to react with the more substituted end, which is a CH2, okay? And so we can draw that one that looks, exactly like that. Is this the only product in this reaction? So this is the only one that I expect to see. So we're going to react on this side. What would that minor product be? So there's the trans isomer. There's also the cis isomer. Yeah, totally. There's a cis isomer as well. So don't forget that. Again, the reason why I'm drilling this in is simply because you have to read the directions. Sometimes Liebens wants all products. Sometimes she wants major. And she typically for midterm 1 asks for all. So if she asks for all, you have to put both. But something that can help you is if you label it. I know that she's kind of lenient if you label it major and minor. Like she'll let you do that, and then like your TA can then grade you based on what was the correct answer. If you don't put these labels, then you kind of put yourself at risk if she just wanted only major, right? But if you put like major and minor, you should be fine. Okay. So again, we react with the CH2. We're gonna make a trans isomer and a cis isomer. Okay. Now the only difference here, this is the exact same center, right? It's secondary. Okay. But and this is also strongly basic, strong nucleophile. But what's the difference between this one and this one? So we can go back here real quick. What's the difference between those two nucleophiles? They're both strongly basic. One is bulky and one is small and one is bulky. So remember that this one here is small. This one over here would be bulky. If I use a bulky base, what is going to change? The reaction's not going to change, right? They both are they're both E2, so the reaction doesn't change. But what changes if I use bulky instead of small? We're going to react with the primary center, okay? And so how many total products should I expect from this here if I react with the primary center? So that might be a tricky question. Let me put it this way. How many unique products would you expect? That one might be easier. Unique meaning different. So there'd be one unique product, that's true, and there would be 3 of them, right? There would be 3 of these, but they're all the same, right? So you would only draw it once. You wouldn't draw all 3 of them, right? Because there's 3 hydrogens at the center. So we're going to react with this center there. Nice. Cool. Here's something that I'll just tell you. If you ever get a question with too much stereochemistry in it, like you notice how this one shows you not only the stereochemistry of I, but also H, just make sure that this is small. Would you guys call this a small base here? So I'll give you that. It's a strong, basic, strong nucleophile. Would you guys call this a small one? Yeah, this is definitely small. Okay. Remember, there's only 2 examples of big, right? There's only 2 examples of big. LDA. So let me actually also write. So she might write LDA for this, and she might write terpetoxide like this for this one. Same thing. They mean the same thing, right, as these here. But everything else is going to be small, right? If you see a small base and you see too much stereochemistry, you know she wants you to do an anti-periplanar type question. Okay, so to ask yourself is anti-periplanar, just look at the leaving group and look at the H. Are they trans? So is it trans in this example? They are. So that means that you're going to redraw everything except for H and I, even the methyl there, and then just draw a double bond. That's your answer. Oops, sorry, I forgot the ethyl there. Okay. Let's say I did this example here. So it's sort of the same. Okay. Are they trans in this example? No, they're not. So you can either rotate it if you'd like to, or what you could do is simply just this. Redraw everything as you see it. And you can actually, even if you wanted to, you could actually put this answer here. All you have to do is switch one side. Either switch this side, so the methyl and the H here, or switch the ethyl and the methyl. I think it's easier if I just switch the ethyl and the methyl. So I'll put ethyl here and methyl here and methyl here. Okay, and that's your answer if it's not already in anti-periplanar state. Okay, I don't think she'll ask you the most complex version of this, where an H is in the plane and I is like dash or wedge. That is actually super hard to predict. You have to actually draw out the rotation. So let me tell you what I'm talking about. So like, for example, imagine she asks you like a question like this one, where I is like here, but H is here. And let's just make it fun. Let me just add a bunch of stuff that is just kind of hard to think about. So let's say you got something like this. If I rewrote this problem like to look like this is actually very easy, as long as H is a dash or a wedge and the leaving group is dash or a wedge, you can either write exactly what you see, right? You either write exactly what you see. What was this? Oh, isopropyl. So in this case, they're both cis. So I just draw what I see, which is this here. Oops. Right? Draw the double bond, and then I just flip a side. So I can flip the methyl and the ethyl. So methyl, ethyl like that. Right? And that's the answer I get, right? As long as they're on the stereochemistry, it's either what you see or it's the opposite. I could even do this again, but now I can make it the way that I want to have it, where now the I is on the wedge. So now that the H is trans to that I, right? And again, it's simply now what I just see. So I'm just going to draw this, this, and this. Put the double bond there, and there you go. See, it's easy to do these two examples. This one's a little more complex. You have to apply a rotation to do it, and so this is how I'll teach you guys to do it. You want to ignore basically the group with the I on it. So you just kind of want to ignore it, and then you want to look at these three guys here. I can redraw the bond stereochemistry as such. Okay, I want to move H to the back here, so H has to go here. That pushes the isopropyl to the wedge, right? It wouldn't make sense if H moved this way and isopropyl moved this way, right? Because they should go in the same direction. So if H is going to isopropyl, isopropyl should move to the wedge, not to the plane. Okay. If isopropyl moves to the wedge, then the phenyl moves to the plane. Then you can redraw, this part back in, and then solve the problem. And so if you look at this one, this is identical to, I guess it's kind of hard to see. So let's just kind of do it. So again, you can kind of just draw what you see here. So I draw what I see. Okay, and then again, I can put the double bond here, but I have to remember that I have to switch two of these groups. I'm just going to switch the ethyl and the methyl. Just like that. And that would be my answer, because the H and the I are cis to each other, right? If they were trans to each other, oh, then I guess, actually, why did I do that? I could have just done this. So let's do that rotation thing again. I realized I could have just moved H to the wedge. I just didn't realize. So let's redo that rotation again. But now we're moving H to the wedge. So if we're moving H to the wedge, the phenyl has to go to the back. It's not going to go, where H was. So you can do this. So H comes here, and then phenyl comes here. Isopropyl then comes over here, right? And then we can redraw in the I group like that. Again, now this is just easier. You just draw what you see. Okay, and that's the double bond we get. So again, I don't think you're going to get an example like this, because Leibniz tends to go easy on you guys for these kind of questions. This is more of like a Nassiri level question, but it's very likely next quarter that you could see this. So it's better to see it now than to have to learn it, completely fresh later on. This is a possibility, but you'll probably get it where it's either cis on the wedge or dash, or it's trans on the wedge or dash. And again, the tricks are pretty, I think, easy for those E2s. The ring reactions, I pretty much did all the relevant ones on that ChemDraw page. So I'll kind of I'll show those to you guys again. These what is this? These 5 ring reactions. These are the only variants of ring reactions you'll ever see in this class. And you just have to understand the idea that rings can't rotate. So stereochemistry is absolute, right? So that's why we have an NR answer, right? If this is the reaction, right? It's going to be NR because the H's are cis to the Br, right? There's no way this can ever take place. Whereas, you know, if they're both cis, then clearly the reaction can take place, right? If one side is dash and one side is trans and one side is cis, the trans side is the one that's going to react, right? So sorry, this is trans and this is cis, right? This side is cis and this side is trans. It's the trans side that reacts. And again, same thing here, right? Like this is this is cis here, and even though we're using a small base, and you would predict that we would make the most stable alkene, right? We're actually going to react and make the less stable alkene or the less subalkene, right? Because the anti-periplanar state can never be satisfied on this side. The only real cool example that Nasiri loves asking this question, I don't know if Levens would ever ask it, is this one here, where you have, you know, it's basically this question here, right? You would think it's NR, but we added in this extra methyl. This extra methyl incorporates a new beta carbon upon which reaction can occur. So it's just like a very neat problem that's just making sure you're paying attention to the definition of elimination, which is beta hydrogen, you know, removal. Cool. We can do a couple more. I think the inversion ones are, you haven't really done any inversion ones, so we'll do a couple of those. Oh, you know what? Let's, yeah, so I guess there was one thing I hadn't really talked about, so we'll talk about that too. So let's say we had this substrate here, and I reacted with N3 minus, and with carboxylic acid. Both this reaction can be in DMF. I'll do DMF this time. This one will probably only be carboxylic acid. Or acetic, this is really acetic acid is the name of that. What could we also do here? I guess we could also do a, it makes it more exciting actually. Let's do that, yeah. We can also do this reaction here. Okay, so once again, right, when we're looking at this, first thing I would note is, well, there's only one substrate. So just ask yourself the question, right? What is the substitution of that carbon there? So what is it going to be? Anyone just say a number, right? It's either 1, 2, or 3, right? Yeah, so secondary, okay? And then we just have to look at the different nucleophiles. So let's focus on N3 minus first. So this is secondary, N3 minus, right? If we go back to the chart, secondary here, right? Where is N3 minus on this list? Yeah, it's weakly basic. So secondary, weakly basic, it's going to be an SN2. Just look out for inversion if it's secondary. Okay, so if we do this, right, what we're going to get is this answer here. What should be the bond stereochemistry when N3 adds on? Should it stay the same or should it invert? Yeah, it's going to be dash. It's going to invert. Totally. Okay, so that's going to be the SN2 answer there. Oh, also, sometimes Levens ask you guys to write what the mechanism name is, so I'll start doing that too. So it's an SN2 reaction. Carboxylic acid is the next one. Where do we see carboxylic acid on here? So where do we see carboxylic acid? Yeah, it's going to be the weak nucleophile or the poor nucleophile, right? And so this is going to be an SN. This is going to be what, a SN 1 reaction. Actually, I'm going to slightly modify the starting material. Actually, no, I can't do that. So let's actually do this then, because I wanted to do something specific here. Let's do this one here. So it's still secondary. Okay. When we do the SN1 here, there is no tertiary carbon next door, nor is there a quaternary carbon. So we won't have to worry about rearrangement. What should be the stereochemistry of the carboxylic acid when it adds on? Should it also be inverted like for the N3? Yeah, so it's gonna be racemic at that center. So not only are we gonna have wedge product, we're also gonna have dash product. So I actually have to include two products here. It's gonna be two of them. Okay. Keep in mind that racemic applies when both things are enantiomers. So would you guys call these two enantiomers? Will we call this molecules enantiomers? Yeah, we would. So we can call this racemic. Okay. But let's say I ask the same question, but with this substrate. Okay. Again, this is we already know what this reaction is. We just did it. But when I draw the two answers here, would you guys call this racemic? Yes, these are diastereomers. Good, good. So remember, racemic only applies if there is only one stereocenter on the molecule, and that's the stereocenter that is changing. Okay, these are diastereomers because yes, this center does racemize. It does turn into R and S, but this center always stays the same. So they're diastereomers. So always be careful. There's a pre-existing chiral center that does not participate. You are not going to make enantiomers, okay? And you cannot say racemic. So these are enantiomers. That's why we can say racemic. Okay, that's why we can say racemic. But these are not enantiomers. So I would always recommend drawing both products and just asking yourself if they're enantiomers, right? If you know, a good way to tell if it's something is an enantiomer is make sure every center inverts. So this center here that I've circled, that inverts, right? Wedge and dash. But this center stays exactly the same. Both centers need to be inverted to be considered a enantiomer, and only one did, so it can't be enantiomeric. Okay, very good. You could get a carbocation shift, not very likely though, so I wouldn't worry too much about that. That's why I really wanted to highlight the diastereomer thing there. That's really what mattered. If we have this here, I mean, I think the example I was just going to use was this one. What do you guys predict is going to be the reaction if it's O minus, RO minus? Okay, so we can go back here. So what would we predict the reaction to be if it's going to be RO minus and it's secondary? Oops. So R minus is a strong base. So what would you predict the reaction to be? Would you agree that it's E2? Yeah, and I would agree. It's going to be E2. In this case, it's symmetrical. They're both CHs, so there's going to be one product. You can just draw what you see. I guess it does. It kind of does matter, I suppose. Oh no, it doesn't actually. Yeah, this doesn't be this. Yeah, this is just the only answer it's going to be. It's symmetrical, so it doesn't matter whether you draw like this or if we draw the other one where it's like this. You'll notice that regardless of what side this isopropyl is on, it's always going to be cis and trans to some methyl group. So no, nothing to worry about there. The whole so the really where this matters, the anti-periplanar state is when both carbons participating are chiral. It's when both are chiral that this really matters. If they're both, if either one is achiral, so notice how this carbon or this beta carbon is achiral, then it doesn't matter how you draw the product. You'll always draw the same thing. Both chirals have to be chiral for it to be an issue about which one you draw for E2. Cool. So one product answer is what we're going to get there. Yeah. Now, I don't know if she'll ever ask you guys this question, but I think it's still a good one to think about. She could ask you stuff like this. Okay, so let's say you had something like this, and you just reacted it with a bunch of different things. I'm not gonna. I guess we can still. It's not a big deal. We can do a little more practice. So NaCN, DMSO. Let's do this. Li, NH2, CH2, CH3. Actually, I don't know why I wrote it out. Let me do this. Oh, this would be NH. Okay. And we can think about this in two sort of scenarios. And I'll explain what I mean by two scenarios in a second. Let's just do this one here. Okay. All right. So let's say we had these four conditions. Actually, let me change this one. Okay, this one might be a little confusing. All right. Cool. If we looked at all these, we can kind of classify what kind of nucleophiles these are. How would you guys classify this guy up here? So look at this guy here. It's like two isopropyls on a nitrogen. Where do you guys see that over here? Yeah, hindered, definitely hindered. So I'll just kind of give it a little bit of this. Actually, let's see how much you guys can remember without looking at that chart. What about NaCN? What would you guys say NaCN? Yeah, weakly basic, I would agree. What about N minus? So NH2 minus. What would you give that? Yeah, strong base, right? That's small. And then what about water? What are we saying water is? Yeah, weak. There we go. Cool. So there's two situations I want to think about this. We're going to think about this in the 1 mole situation. And then we're going to think about this in the excess mole situation. The difference between excess mole and 1 mole is that 1 mole will only react with the most reactive spot. And excess will only react at everywhere it can possibly react. Okay. So either we're reacting everywhere or we're reacting at the most reactive spot. Okay. Which is kind of a, it's a little bit of an interesting question to ask. So the easiest one I think to start with actually is going to be the weakly basic. So we think about this guy. This guy mainly does what reaction? So when we think of the reaction that a weakly basic does, what is the main reaction that this guy does? SN2. So that means that in a 1 mole situation, it's probably going to do an SN2 reaction somewhere. Now, which leaving group do you think is going to be the center that we attack if we're doing an SN2? Keeping in mind what makes the best SN2 possible. So think about what makes the SN2 reaction faster. And so someone says the I center. Sorry, I just dropped my. So if it's the I center, right? Why did you choose the I center? What is true about the I center that makes it the most ideal for SN2? So back here, did we ever look at anything in terms of solvent? Do any of these factors here ever talk about solvent? Or like, do you even see solvent even mentioned anywhere here? No. So solvation, all that stuff, solvent, aprotic, protic, none of that matters. All we care about is really two things: what kind of nucleophile we have, and what is the substrate. What is the substrate substitution? Okay, so we know we have a weakly basic, and again, weakly basic SN2, right, SN1 down here. So what does that tell you about substitution? Which substitution do you think is the best for SN2? If going down eventually gets to SN1, what does that tell you about SN2 up here? Is it fast or slow? It's fast. The less alpha substitution you have, the faster the reaction is, okay? And so that's why, right? We are definitely reacting in the 1 mole situation with only the I center, because it is the least hindered center out of all of these, okay? And all of this stays the same. Now, in the excess mole, we are going to react with every center we possibly could react with, okay? And let's keep it reasonable. Let's say that only SN2 reactions will work here in a reasonable amount of time. Actually, no, I guess that, I'm not sure. I guess that's up to Levens if she wants to make that, so I'll leave that up to her. But if we had to say where things could react, where else would you guys do a reaction? Could we do it at the OTS? Yeah, OTS is a good leaving group. That's secondary center. SN2 works at secondary. We could totally see that happen there. Okay, let's make this a wedge just so we can have a little more fun, right? That's a wedge. What does that center turn into? Is it racemic or is it specifically something? Yeah, it's going to be dashed. Okay, so CN is going to be dashed here. What about this bromine center? You guys think anything could reasonably happen at that bromine center? No, probably not. So this is like, I'll leave this up to Levens. Technically there is a reaction, but it's not SN2. And I think that she would want you to just assume that it's so slow that it's not going to happen. Okay, that's what I would think she would want you to assume, because that's what I would assume. So I'm going to not put a reaction there. Okay. I'm not going to do a reaction there, but you should definitely ask her too if she would want you to do an SN1 reaction, because technically there is an SN1 that could occur there. What about the alcohol? Do you guys think anything can happen at the alcohol? What are we thinking about the alcohol? Yay or nay? Oh, someone said no. No, you're right. Not at all. Okay, because alcohols are bad leaving groups. And so we're not going to expect any reaction to occur in terms of a substitution or an elimination. Okay, cool. So 1 mole we'll put on the left side, excess mole we'll put on the right side. Let's do the weak nucleophile next, right? If we're in the 1 mole situation, which center do you think reacts the fastest? So we know OH we just says the worst leaving group, so I'll keep it back in here. So right now we're just thinking about the 1 mole. We can think about the excess mole in a second. But what do we think about the 1 mole? Oh, for the previous one. Oh, sorry. I didn't realize. I thought I changed it. Yeah. So what do we think about the 1 mole for water? Is it going to react to the I, at the BR, or the OTS? So someone says the BR. And so why did you choose the BR? What were you looking at for the BR? Yeah, it's a tertiary carbon. That means it makes the best cation possible. You're definitely seeing a reaction there. Okay. And what would you say about the center? Do you think that it matters if it's dash or wedge on that center, like it did before? So does it specifically have to be dash or specifically have to be wedge? Um, yeah, exactly. Yeah, exactly. So it's going to be either dash or wedge. So it doesn't matter. There's actually a notation for this that I'm going to use here. If you specifically make this line, I wouldn't do it on an exam. I'm just doing it now. If you make this line, you're basically saying it could be wedge or dash. Okay, it's not a hash it's not a dash symbol. It's this like specific squiggly line. And that squiggly line is basically telling you that it could be, either dash or wedge. And you're totally right. Because of the OTS center, you don't want to say that this is enantiomers. It's definitely going to be diastereomer. Okay. Again, primary is never going to react. The secondary, right? How do we feel about secondary? Do you think the secondary could react in the excess example? What do you guys think? So if we're thinking about the excess mole example, right? So we know that I won't react because it doesn't react with primaries. But what about the secondary OTS center? Is that going to react to the excess mole? Yeah, it will, right? Because secondary cations can exist. Now, here's the interesting thing, is that this secondary cation, right? Do you think it will rearrange? So this is a really hard question. So it's okay if you guys don't get this or not. But typically when we think of rearrangements, we think of hydrides or we think of methyls, right? There's neither a hydride or a methyl on this carbon. So you wouldn't really be expected to shift here. It would really end up, it would come down to what is experimentally observed for this system. So because of that reason, we won't do a shift. But just remember in general, if there's a methyl or a hydrogen, we want to do a shift if that, if we can do that, like secondary or tertiary. I'm just not going to do it here because again, neither of those exist. So it's, we can't really assume if it'll happen or not. Okay. So we're just going to go ahead and also make this like a squiggly line here at the OH reactor, like it'll add there too. But yeah, that one's a difficult one. You probably want to get something like that on an exam. Okay. And so that's the answer there. Cool. All right. Strong base. Where do you guys think that this is going to react first? This one might be. This is going to be interesting. Let's see what you guys can think of. Where do you guys think this is going to react first? Interesting. So someone says OTS or I. Okay. I think those are great guesses because it looks like you're going for primary, secondary. This one's a really hard one too. I should have thought about this before I wrote this. When it comes to eliminations, especially of small bases go for the more subproduct, right? You typically want to make the more subproduct. So where do you think we can make the more substituted alkene? So there's like, there's ethene, there's propene, there's butene, there's this guy, and then there's this guy. If we think about the most substituted thing possible, it's definitely going to be on the bromine. Okay, bromine is what's going to leave. Now here's kind of the hard thing is that you don't know if it's going to go to the left or the right because that makes diastereomers. So I'm only going to include one here, but I'm going to put plus diastereomer because it could be either to the left or the right there. Okay. So that's kind of a hard one. Should have thought about that before I wrote it. But it's a good thing to think about, right? When would when would E2 be selective? It would be kind of selective there. Cool. In terms of excess mole though, right? Do you guys think that there's any limitation here for where this can react? Other than OH, do you guys think that E2 is going to be limited if there's excess moles of base or excess moles of this guy? Do you think any of these centers are not going to react? Yeah, I would agree. I would agree that it can react at all centers. Okay. Now here's the interesting thing, right? Let's say I either make this double bond here or this double bond here. When OTS reacts, it always makes this double bond here. Why might it always make that double bond? So why does it opt to make the less stable double bond? What do you guys notice about these two double bonds? I'll give you a hint. There's p orbitals in this double bond, and there's p orbitals in this double bond. What do you guys notice? Yeah, it's going to be conjugated. It's going to be conjugated. So it's going to be incredibly stable. That OTS center will react a lot faster than the I center reacts. Okay, so order of reaction would have been BR, then OTS, and then the iodide. And then there's the diastereomer where the double bond forms on the other side. Cool, cool. I actually, now I don't want to do this one because then now this one gets a little bit tricky. So I'm just going to give you the answer for this one based off of the eliminations answers here. Really, the only difference become if the 1 mole example was the tertiary sub for the small base, the big base is going to make the primary sub first, right? Because it's just bulky. That's what it's going to do. In the excess mole example, if you really pushed it to, the base could really eliminate everywhere. It's just gonna get, I'm gonna put a question mark here because it gets a little complicated. I should have thought about how I did this earlier, but it'll get a little complicated if we're doing this with these substituents here, because there is the conjugation of the double bonds that actually makes it very likely that these guys could form first, or sorry, these guys could form very easily. I think that there would be some issue with the tertiary. Cool. So I've never seen her ask a question like this, but I think Nasiri will definitely ask you questions like this next quarter, because the first chapter you learned in 119B is on alkenes. So you revisit elimination, you revisit all this stuff anyways. And Nasiri loves to ask 1 mole versus excess mole reaction questions. So it's always a good thing to think about what is the most reactive center in the case that, you know, should it ever show up. Okay, cool, 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 cool. So that's all I really had for predicting the product and stuff. I think, again, really, I think you guys are probably going to be prepared as long as you understand how to use this table. And then the intricacies of E2, really, it's really the intricacies of E2 that's the issue. Most predictive products are pretty hackable. Let me show you guys this one, though. So this is the hindered primary with the weakly basic weak nucleophile. The way that this works is if we have something like this, or if I have something like this, and I introduce both of these to water, what ends up happening is you get a concerted shift where the cation you form will form at the same time that something shifts. So normally you form a cation and then do a shift, right? Well, this time the cation forms after you do a shift, okay? So you don't have a carbocation formation until the shift is done. This is what you would, oh, sorry, I think this should be this, and then this should be this, yeah. So these are the two substrates you would kind of expect. And then after addition, right, you either get this alcohol or you get this alcohol here. Okay, so this is the concerted ship that I was saying is the exception to SN1E1, because these are primary centers. They're just hindered primary. I know Levens for sure goes over this one. This was the one that she doesn't really go over, but it still kind of counts because it's like a hydride instead of a methyl. Okay, but these are categorized concerted shifts. That's really what falls under this one. Sorry, this one here. Okay, but again, just as long as you can navigate this list, you'll probably be fine for reactions. Reactions really is like the hardest thing on this exam. You know, I think IR is actually pretty, if you just watch a couple of IR videos or just, you know, look at a couple IR spectra, it's actually really easy to do IR. You just have to identify what's on the, what is in the spectra and what does it mean. But yeah, so just take some time, you know, even try writing your own reactions and see if you can solve them and then use the chart to solve them, right? That's really where you want to go with that. So that's all I really have to say about reactions. I think you guys are going to be fine for the most part. Cool. So it's about to be 8 o'clock, which is, you know, I think it's a great time. If you guys want, we can stop here. If there's any like specific other, you know, topic you guys want me to talk about, there's still time. I could still talk about something, but the main thing I wanted to talk about was this, because I think when I looked at someone sent the list of, what was it? Someone sent earlier, like the list of all the things that's going to be talked about. That's really the most important stuff. I think it's like, I mean, in that list, let me see. It's like, it starts from, yeah, so there's chirality. I'm not sure how many of you guys watched the chirality video, but I think that I did a good job on that one. That covers all the chirality stuff. And then this here would cover everything up till alcohol nomenclature. Oh, what the heck? So you guys actually do need to know how to do some alcohol stuff. That's interesting. Okay, then actually we have to go back and do something real quick, because there's one thing we have to account for. So actually, I thought this was going to be on the final, which is why I didn't mention it. But there's actually, we have to change actually 2 of these answers. It's going to be this one and this one. If you ever have a strongly basic nucleophile in the presence of an alcohol functional group, do any of you guys remember the pKa of an alcohol? Yeah, it's like 15 to 18. So I'll just use 16. That's a good number. This guy has a pKa of 35. And so does this guy. It's like a pKa of 35. So what does that tell you will happen if this has a pKa of 35 and this has a pKa of 16? So let me ask you this question. Who carries the minus charge better? The guy at 16 or the guy at 35? Who carries the lone pair better? Yeah. So who carries the lone pair better, N minus or O minus? If 16 is the better number. O minus. That means that actually the very first thing that happens at 1 mole is a deprotonation on the alcohol. This is actually what's the first thing that's going to happen. Normally I don't talk about this until final, but it looks like, I guess in the summer things are a little bit sped up. You do need to talk about that first. So again, anytime you use a strongly basic nucleophile, whether it's big or small, the first thing that can happen, if it can happen, it will be acid base. Acid base is like 1,000 times faster than any substitution or elimination reaction. So anytime you see an alcohol molecule on anything, if you see a strongly basic nucleophile, consider that acid base can happen. Now, you don't have to worry about this for weakly basics, right? Whether it's a strong nucleophile or a weak nucleophile and it's weakly basic, because these guys don't like protons in general. So CN minus doesn't want a proton and neither does water, right? That's why for these two, we don't have to consider that. But for these guys that are strongly basic, you do have to consider the fact that the first thing that'll happen is a deprotonation. Okay, so we have to actually modify what will go on in both these cases. So I'm happy that I actually looked at that again. So that means that you're definitely guaranteed one problem on your exam. Ooh, you know what? This is guaranteed. This is guaranteed. I'll guarantee it. You're gonna get a problem like this. It's gonna be something like this, and it's gonna be like any. It's gonna be like any NH2 or some strong basic nucleophile. Okay, it's gonna be something that's strongly basic, strong nucleophile, strongly basic, and a bunch of you guys, a bunch of people on the exam are gonna do this. They're gonna see bromine and OH, think that OH is a bad leaving group and bromine's a good leaving group, and they're gonna do the E2 reaction here because it's strongly basic. So they're gonna give these two answers. Oh man, I could totally see her doing this too. But this is wrong. This is not the right answer. The correct answer would actually be this. It would be O minus. Okay. Well, actually, I suppose you